Hello there, welcome to Ethio Hahu tutorial. I'm Getachew, and today we are going to see about simple harmonic motion. An oscillation is simple harmonic motion when the net force along the direction of motion obeys Hooke's law. We know from Hooke's law the elastic restoring force is equal to minus k times x. If this condition is fulfilled, then the oscillation is said to be simple harmonic motion, because the restoring force is directly proportional to the stretch of the spring and directed towards the equilibrium position. Having said, let's consider this mass spring system with a spring having force constant k, and let's consider this point is the equilibrium position and this is the maximum point of oscillation. X is equal to a and x is equal to minus a. As this block oscillates back and forth or to and fro about the equilibrium position, there is restoring force. This restoring force restores a system displaced from the equilibrium position towards the equilibrium position. Therefore, this restoring force is equal to minus k times x. And from Newton's second law, we know that net force is equal to mass times acceleration. In this case, the only net force acting on this block is the restoring force. Therefore, the net force is simply the restoring force, which is equal to mass times acceleration. And this implies acceleration is equal to restoring force divided by m. And since the restoring force is given by minus kx is equal to minus k times x divided by m, therefore the acceleration of the block is minus k over m times x. Here again, the acceleration is directed towards the equilibrium position. When x is equal to 0, the acceleration is 0. That means the velocity is maximum, because if we have velocity versus time graph curve, then at the maximum point and at the minimum point, the acceleration is 0, because this is velocity axis. At this point, the slope is 0 or the derivative is 0. Therefore, when x equals 0, the acceleration is 0 and the velocity is maximum. When x is maximum, x max means amplitude, then the acceleration is equal to minus k over m times a. Therefore, the acceleration of the particle is proportional to the displacement x and directed towards the equilibrium position. Let's consider energy exchange. Consider the following mass spring system. This is a block of mass m attached to a spring of force constant k, and assume this is the equilibrium position, x is equal to 0, and this is the maximum point of oscillation, x is equal to a and x is equal to minus a. The block oscillates about the equilibrium position back and forth, and let's consider this point is a, this point is c, and this point is b. A is the point at the equilibrium position, b is the maximum point of oscillation, and c is any point between the lowest point of oscillation and the highest point of oscillation. And here again, assume friction is 0. In the absence of friction, mechanical energy is conserved. That is, mechanical energy at A is equal to mechanical energy at B is equal to mechanical energy at C. Mechanical energy at point A is the sum of all kinetic energies and potential energies. Here, since there is no rotational motion, we ignore rotational kinetic energy, and since the block moves along the same level, the gravitational potential energy is constant, and the change in gravitational potential energy becomes 0 as it moves from A to B or B to A. Therefore, mechanical energy at point A is simply kinetic energy at point A plus elastic potential energy at point A, which is equal to mechanical energy at point B is kinetic energy at point B plus elastic potential energy at point B. Since at point A, x is equal to 0, elastic potential energy is 0 because elastic potential energy is half times k times 0 square, which is equal to 0. At point B, the speed is 0 and kinetic energy is equal to half times m times v square is equal to 0. Therefore, elastic potential energy at point A is 0 and kinetic energy at point B is 0. Therefore, kinetic energy at point A is half times m times v naught square is equal to elastic potential energy at point B is half times k times a square. Half goes with half. M times v naught square is equal to k times a square, where v naught is maximum speed. Dividing both sides by m, v naught square is equal to k over m times a square, and v naught is equal to the square root of k over m times a. This is the maximum speed at which the block passes the lowest point of oscillation. As it passes through the lowest point of oscillation, it has a maximum speed. V naught is equal to the square root of k over m times the amplitude, and this is maximum speed. Now, considering point C and point B, again, mechanical energy at point C is equal to mechanical energy at point B. Mechanical energy at point C is simply kinetic energy at point C plus elastic potential energy at point C is equal to mechanical energy at point B is kinetic energy at point B plus elastic potential energy at point B. Kinetic energy at point C is different from 0 because at point C, the particle has a speed. The speed of the particle as it moves from A to B gets smaller and smaller, and 0 when it reaches point B. But at point C, it has some speed. Hence, half times m times v square plus elastic potential energy at point C. Say this is x. The distance from the equilibrium position is x. Half times k times x square, which is equal to kinetic energy at point B is 0 because when it reaches point B, the speed is 0. And we have only maximum elastic potential energy, half times k times a square. Since both sides we have half, half goes with half. And m times v square is equal to k times a square minus k x square. Dividing both sides by m, v square is equal to k over m into a square minus x square because k is common for a square and x square. Taking the square root of both sides, v is equal to plus or minus the square root of k over m into a square minus x square. This is the velocity of the particle at any point between the lowest point of oscillation and the highest point of oscillation. And the velocity of the particle at any position x is equal to plus or minus the square root of k over m into a square minus x square. When x is equal to 0, the velocity of the particle is v naught, which is equal to the square root of k over m times a because the square root of a square is a. When x is equal to a at the maximum amplitude, v is equal to plus or minus the square root of k over m into a square minus a square. A square minus a square is 0, 0 times a number, which is equal to 0. Therefore, at the maximum point, the speed is 0, but at the lowest point of oscillation or at the equilibrium position, the speed is maximum. This is maximum speed. In general, the restoring force is given by minus k times x from Hooke's law. The acceleration of the particle as function of x, this as function of x, is equal to minus k over m times x, and the velocity of the particle at any position x is equal to plus or minus the square root of k over m into a square minus x square. Now, let's draw energy versus position graph. This x-axis, this is energy axis. This is 0, this is x is equal to a, and this is x is equal to minus a. And this is total energy, which is equal to kinetic energy plus elastic potential energy. And this point is the equilibrium position A. The highest point of oscillation is B. And the point between the lowest point of oscillation and the highest point of oscillation, C. At point C, we have both kinetic energy and potential energy. This is elastic potential energy, and this gap is kinetic energy. And the sum of elastic potential energy and kinetic energy is simply total energy. As one moves from the lowest point of oscillation to the highest point of oscillation, this gap increases. The elastic potential energy increases. In turn, the kinetic energy gap decreases. And at the maximum point of oscillation, we have maximum elastic potential energy. This gap is maximum elastic potential energy, that is half times k times a square, and 0 kinetic energy. But if one moves from point B to point A, from the highest point of oscillation to the lowest point of oscillation, this gap gets smaller and smaller, and the elastic potential energy gets smaller and smaller. In turn, the kinetic energy gap increases, and when it reaches at the lowest point of oscillation, the kinetic energy gap is maximum. Therefore, at the lowest point of oscillation, the particle has maximum kinetic energy. At the highest point of oscillation, the particle has maximum elastic potential energy. But in between the lowest point of oscillation and the highest point of oscillation, the particle has both kinetic energy and potential energy. And the sum of this elastic potential energy and kinetic energy is equal to total energy. Now let's compare simple harmonic motion with uniform circular motion. To compare simple harmonic motion with that of uniform circular motion, let's consider a point C. This point C around a circle of radius A, moving with constant speed v0 as shown below. This point C is moving with a constant speed v0 around this circle of radius A. And the projection of point C on the x-axis is P. When this particle moves in a counterclockwise direction, the projection of point C on the x-axis moves back and forth about this point. When this particle, point C, reaches this point, the projection of point C on the x-axis is this one. When this point C reaches, say this point, the projection of this point C on the x-axis is P. This particle moves to this direction and reaches this point. When this point C reaches this point, its projection is the same as the point itself. When this point C reaches, say this point C, the projection of this point C on the x-axis returns to its initial direction. It moves to this direction. When this point C reaches, say this point, the projection of this point C on the x-axis becomes this one. And when it reaches this point on the x-axis, the projection coincides with the point. Therefore, for every revolution of point C, this point P moves back and forth once. Therefore, the motion of this point P is similar to that of the mass spring system for every revolution. that point C performs, point P moves back and forth along the x-axis. Therefore, the motion of point P is similar to that of simple harmonic motion. Therefore, the motion of point P is similar to that of simple harmonic motion of mass spring system that we have seen so far. Let's find x, the position of this point P from the equilibrium position. Hence, x is equal to a times cosine of theta, because this is right angle triangle. But theta is the angular displacement made by the particle, and theta is equal to omega naught times t. But what is omega naught? Omega naught is the angular frequency of this point C, 2 pi over period times t, and 1 over period is frequency, 2 pi frequency times t. Therefore, x is equal to a times cosine of theta is 2 pi ft. This is our first equation. The position of simple harmonic motion from the equilibrium position as function of time is x is equal to a times cosine of 2 pi ft, where a is the amplitude of oscillation of simple harmonic motion. Next, let's find the speed. To find the speed v of point P, we use this. V is this one, the velocity of this point P along the x-axis is similar to the component of v naught along the x-axis. Therefore, v is equal to simply v naught times, if this angle is theta, this angle is theta, this is 90 minus theta. This angle is 90 minus theta. Therefore, v naught times cosine of 90 minus theta. But this v points to the negative x-axis, and we put negative sign here. V is equal to minus v naught times cosine of 90 minus theta is simply sine of theta, because 90 minus theta and theta are complementary angles. If two angles are complementary angles, then the cosine of one is the same as the sine of the other. Therefore, cosine of 90 minus theta is the same as sine of theta, because theta and 90 minus theta are complementary angles. And this is equal to minus v naught sine of theta is 2 pi f times t, that we have already found. But what is v naught? From the relationship between linear quantity and angular quantity, v naught is equal to r times omega naught. This implies v naught is equal to r, the radius of circle is a times omega naught. Therefore, for v naught, substitute a times omega naught. V is equal to minus omega naught times a sine of 2 pi ft. This is our second equation. Next, let's find the period of revolution of this point C around this circle and the period of oscillation of this point P once along this path, along the x-axis. To find that, let's consider this. From V at any position x is equal to simply the square root of k over m into a square minus x square. V naught is equal to velocity at x is equal to 0 is equal to the square root of k over m times a, because when x is equal to 0, this goes to 0. The square root of a square is a times the square root of k over m. Now let's find the period of revolution of this point C. The period of point C to move once around the circle of radius a, period is equal to simply the distance traveled by this point C is the circumference of circle 2 pi times r divided by v naught. V naught is the speed of revolution, but this is equal to r is equal to a, 2 pi times a divided by v naught. Since we have found v naught is equal to the square root of k over m times a, so far the period of point C to move once around this circle is equal to 2 pi times a divided by v naught is the square root of k over m times a. A goes with a, and this is equal to 2 pi times the square root of m over k. Therefore, the period of revolution is 2 pi the square root of m over k, and the frequency of revolution is 1 over 2 pi the square root of k over m. This is the period of revolution, and this is the frequency of revolution. And this is the period of simple harmonic motion. This is period of simple harmonic motion. To find the acceleration of point P, the acceleration of oscillation of this point P along the x-axis is obtained by finding x component of the centripetal acceleration of point C. Even though the speed is constant, there is a continuous change in direction of the velocity, and due to this change in direction of the velocity, we have centripetal acceleration, and the direction of centripetal acceleration is towards the center of circle. This is centripetal acceleration. This centripetal acceleration has two components. One is vertically downward component, and the other is a component which is directed towards the negative x-axis. And the component of the centripetal acceleration directed to the negative x-axis is ax, and this ax is the same as the acceleration of point P. Therefore, ax is equal to simply ac, centripetal acceleration, times this is 90 minus theta. Therefore, ac times sine of 90 minus theta, but here negative. This implies ax is equal to minus ac, centripetal acceleration is v naught square divided by r, times sine of 90 minus theta is the same as cosine of theta. And here theta is simply 2 pi f times t, and r is equal to a. Therefore, the acceleration of point P is equal to minus v naught square over a times cosine of 2 pi f times t. Again, v naught is equal to r times omega naught, or a times omega naught. Substitute for v naught. A is equal to minus omega naught square a square, because v naught is the same as a times omega naught. V naught square is omega naught square times a square divided by a times cosine of 2 pi ft. 1a goes with 1a, and this is equal to minus omega naught square a times cosine of 2 pi ft. But a times cosine of 2 pi ft is x. Therefore, acceleration is equal to minus omega square times x. This is our third equation. Now, let's find the period of oscillation of point P. We have found the period of rotation of this point C, but let's find the period of oscillation of this point P. For every revolution of point C, this point P oscillates back and forth once along the x-axis. Therefore, they should have the same period. The period of revolution of point C is the same as the period of oscillation of point P. To find that, we know that acceleration as function of x is equal to minus k over m times x that we have found so far, and from 3, acceleration of x is equal to simply minus omega naught square x. This implies minus omega naught square times x is equal to minus k over m times x. Here minus goes with minus, x goes with x, because these two are the acceleration of this point P. Omega naught square is equal to simply k over m. Omega naught is equal to the square root of k over m. But omega naught is 2 pi over period is equal to the square root of k over m. This implies, let's bring this k, the square root of k over m here and take t to the right. T is equal to 2 pi over the square root of k over m. This is equal to 2 pi the square root of m over k. Therefore, the period of oscillation of this point P is equal to 2 pi the square root of m over k, and this is the same as the period of rotation of this point C around the circle. And this is how simple harmonic motion is related to that of uniform circular motion. This is all about today. Next, we'll do exercise on this. Until then, have a nice time.